I'm really excited about today, but before we get started, let me just do a couple of housekeeping items. Number one, if you can please sign or sign on a piece of paper, it really helps because then we can take that back to the IEEE and let them know who's involved. The second thing to note is next month's talk is on November 18th, and it's People's Co-op Energy, and they're going to talk about energy in the local area. So look forward to that. And then in December, we're still working on our science movie night, and you'll have more information about that as it comes along. So today, it's my pleasure to introduce David Lovett. I first found David on his YouTube channel where he worked with vintage computers, and I was absolutely fascinated, not just by the computers, but by David himself and his knowledge base, which is really incredible, particularly given that he was not specifically trained as an engineer. And you'll hear more about that later. He's really tackled a number of really interesting projects and made, fairly complex architecture really accessible to the audience. And so today he's going to talk about some of that experience and maybe some of what he does on a day-to-day or week-to-week basis through his website or through his channel, which is Usagi Electric. Let's give him a round of applause.
Turn the mic on here. All right. Hello. Good morning. It's not morning, but feels like that to me. As he said, my name is David Lovett, and I want to be ultra clear. I am not an engineer. You guys are all very brilliant people, and it feels very awkward for me to be standing up here giving a talk to you. But I figured I would start with just talking about who exactly I am, if my clicker here would actually click. So we're going to start right off the bat with the most awkward photo possible, which is baby pictures. Buckle up. We're starting with baby pictures. No, I'm showing this picture. That is actually me at 1 year old. But I'm showing the picture not because I want you to look at me. I want you to look at what I'm standing in. And I'm standing in a 1967 Austin Healey 3000 Mark III. One of the most beautiful cars ever made. And it started at a very young age. And 40 years later, same car, same idiot, right behind the wheel, driving it like a moron. I was born and raised a car guy. My dad had that 67 Healey. He had a 64 Mustang, 289 V8, 4 on the floor. I put it on its roof when I was 17. So, wonderful history with car guys. Fast forwarding through high school after I crashed the car, I went to the University of North Texas. So I am born and raised in Texas, and I went to the University of North Texas to study computer engineering, where I very rapidly flunked out. And that's no joke. It turns out that if you don't go to class, you can't pass class. And I had a buddy that lived nearby the university, and he had an Xbox, and I played a whole lot of Halo, which, yeah, can't pass. So my parents said, this is not working. They put me on an airplane, and they sent me all the way around the world to Kanazawa, Japan. They knew that I had a bit of an interest in Japanese culture and society and learning a bit about it. And so there I am, 19 years old, looking out over the beautiful city of Kanazawa, Japan. And I attended a language immersion program. So it was 4 hours a day, 5 days a week of just studying the Japanese language. So when I came back, I had a little bit of direction in my life now. I was kind of aimless up to that point, and this kind of got me focused. I went to the State University of New York at Albany, which is one of the coldest places on the entire planet. The weather was miserable. But I majored in Japanese with a minor in Korean. So as I said, I'm not an engineer, I'm a linguist. So that's what I am trained in. I did a whole bunch of work in Japan, actually. So after I graduated, I moved back to Japan, and I worked with a vendor for a large automotive manufacturer in Japan. And for that vendor, I would do a lot of Japanese to English technical translation. And ultimately, that grew into doing technical training in interesting parts of the world. We've done training in Bahrain, we did training in Dubai, Taiwan, Thailand. So I got to see a lot of really cool places, but all of this is driving home the fact that I am immensely tall. That's a standard Jeep that you're looking at right there, and I'm like 12 and a half feet tall. No, that was a hilarious picture. But all of this is building up to the fact that I'm a car guy. I have built up this insane collection of cars. Not insane is that they're cool, insane that I've spent far too much money on them. You don't want to add it all together. It's terrifying. This is just half of the collection. There's a full another 5 cars beyond that that didn't fit on the slide. For those that are just real quick, those are curious. It's an 88 300ZX, a 7080 Isuzu 117 Coupe, 73 Isuzu Bella, and a 67 Mitsubishi 360. That one is a 360cc inline 2-cylinder air-cooled 2-stroke. The whole car is about the size of this table. It's tiny. It was a K car from the 60s in Japan. So this is all to really drive home the point that I'm not an engineer. I'm not even a linguist. I'm a mechanic. I work on stuff. That's what I like doing. And I did this job of technical translation and technical training and working on cars and doing all of that right up until something happened in the year 2020. Everybody was affected by this, and I was affected in the way that my job evaporated, essentially overnight. I flew to Tokyo in February of 2020 for a job. I was actually on loan to Subaru for that job. I landed, I got off the plane, I'm walking around the streets of Tokyo. My boss calls me and says, by the way, the event might be canceled. I'm like, you couldn't have told me this 14 hours earlier? Because just got off the airplane, my man. And sure enough, the guests from South America that were supposed to fly into Japan said, nope, we're not going. This Corona thing seems quite scary. And that was it. I flew home from that, and I didn't get any more work for the next 4 years. So at the beginning of 2020, like we all thought, like, it'll be over in 3 months, right? So I sat on my thumbs for about 3 months, but you can only sit still for so long. So I had to do something. I had to find a hobby, and classic cars is been fantastically expensive. You just did pour money into it and get nothing in return. So we had this old teletype. I don't know if anybody's familiar with a teletype. This was a way to send text information using essentially digital encoding. So they had something called 5-bit Baudot, and it was serial data that you would send anywhere in the world, and you could send it with teletypes. This particular one is from about 1924, 1925. We got this from a neighbor when I was like 5 years old, and it's been in the garage ever since. So I sat down and I decided to restore it, and I got it going. It was something I could do for cheap, easy, and fun, and that itself led into, hey, maybe I should start filming this stuff. And so I started the YouTube channel called Usagi Electric. And a lot of people ask this question. They wonder what USAGI stands for. It does not mean United States of America government issue. Usagi is just the Japanese word for rabbit. I have a pet rabbit. I like rabbits. I like cars. I like electronics. I mean, it's, Usagi, naming things is the single most difficult thing in the world, all right? But it's grown. I'm closing in on 100,000 subscribers. We've got more than 10 million total video views. And I'm going to talk a bit more about the YouTube side of things a little later. But I want to talk about kind of some of the things that I work on that channel. Most notably, probably my biggest project, the one that I'm most proud of and the one that's been around for the longest, is a project that is now 3 years running. And it's this thing, the Centurion mini computer. By the way, you can see behind it is that 1967 Austin Healey 3000 Mark III. It's been in the family longer than I have. But this is a computer that I found on Facebook Marketplace, and it doesn't look like much of a computer right there. But I figured that when I saw it on Facebook Marketplace, I saw all the terminals, I saw the racks. I was like, hey, I can probably make a quick buck out of this. I can turn this around. Or if it's interesting, I can work on it. And so it looks like a basket case because it was a basket case. This is the building that it was in when I went up to Oklahoma to pick it up. You can see half of the roof is missing. So the scrappers that own that building would go and buy junk lots, and they would push everything into the half that had a roof. But there's no wall. Like there's no wall between the two. So like if it just rained a little sideways, rain would come in. So here I have this computer from the 1970s that had been faithfully used at a place called Glenn-Smith Oil and Gas Company, and then sold for scrap, and then pushed into a corner of a warehouse that didn't have a roof. And I had this crazy notion to pull it home and try to restore it, not really knowing anything about mini computers. And I mean, it's huge, right? So that first picture kind of showed it all spread out. We did manage to get it all stuffed into the back of our truck. We were riding on the bump stops the whole way home. This thing had 2 hard drives. You can actually see one of the hard drives kind of right in the middle of this open cabinet on the front here. That hard drive weighs 135 pounds and has an insane 10 megabytes of storage. And that's not even on a single, that's on 2 platters. So you have to address the 2 different platters separately within the operating system. You only really get access to 5 megabytes at a time. The other drive in the back is a lot bigger. It was a 96 megabyte drive, so that was a big upgrade. And it's like 190 pounds. It's even heavier. The printer is over 200 pounds. I mean, it was like, we pushed the truck to the limit there. The drives themselves were not in good shape. We have this term that say, I crashed my computer. The kind of vernacular these days means that the computer has stopped working and I need to hit reset and reboot into the operating system. But that term, I believe, I may be wrong on this, I'm saying this, but that term comes from an actual crash where the heads on your hard drive actually strike the platter. And when that happens, the heads make contact with the magnetic material and they shave that magnetic material off, and your data floats off into the ether. It never comes back. And both of these drives were crashed. The one on the left is called a Hawk drive. The one on the right is called a Phoenix drive. The Hawk drive had crashed so hard that the heads themselves had been ripped in 2. I've never seen a hard drive crash that hard. So here we are with this machine that is undocumented. It was called a Centurion mini computer. You get on Google, there's no information about it. There's no documentation. The CPU is completely unknown. The drives had data on them 3 decades ago, but they're unsavable. So this feels like we've hit a wall. Where do we go from here, right? The drives, we can't save it. There's no documentation. I have no idea what any of these cards do. I mean, I do now because I've spent 3 years with it. But at the time, that was like a total mystery. So what do? You hunker down, you get to work. We made our own documentation. We sat down and reverse engineered the entire thing. And I say we, it's not, I did very little of this. It was a group of very intelligent people on the Discord that got to work with me. And so when I say we reverse engineered the CPU is a card that's about this big by that tall with about 85 ICs on it. It's got a lot. It's based on the AM2901, which is a 4-bit bit slice ALU, and it uses microcode. So it has 7 ROMs on there that have a 56-bit micro word, whatever. It's all quite complex. So what we did is we pulled the microcode off of those ROMs. It was still intact. That was good. And we had somebody going through trying to figure out what that microcode meant. And then me and about 3 other people over the course of 2 months sat down with a multimeter and a Zoom meeting and beeped out every single connection from every single IC to every single other IC. And since we could read what the ICs were, this is an AM2901, this is a 74LS04, this is an LS06 or whatever, we knew then how the logic all connected to each other, which means that we could then create something like this, which is a block diagram of how the CPU on a Centurion operates. So this kind of reverse engineering effort, which took, it may sound like this happened very quickly, it took like a year to figure this stuff out, helped us get our foot in the door. But all during that time, you know, it's not just the reverse engineering effort. I'm a hardware guy. Like I said, I'm a mechanic. So I'm out there like swinging hammers and turning wrenches and trying to get this thing going. And while I'm in the middle of that, a former employee that used to work at Centurion Computers, Centurion turns out was a local company in Richardson, Texas. And this is him. This is the dude. This is Ken Romain. He reached out and got in touch with me. And this is him building Centurion mini computers in the mid 1970s at Centurion headquarters. This is his picture he sent to me, which I thought was like really awesome. So he reached out, he got in touch with me, and we started getting to work. You can see that that's him. He's put on a little bit in the midsection. But this is us carrying one of those hard drives. Through mutual acquaintances, we came across another hard drive. We were able to bring it back to life. So we had a unrelated Hawk drive come back to life. We actually got it spun up. We got the heads flying. We needed to do a head alignment, which is what we're doing right here. And we're doing it kind of the hard. There's a lot of excitement going on right there. So we did a head alignment. We started reverse engineering some of the code, getting custom software running to pull the data off of platters. We got data off the platters. We started figuring out what's going on. We figured out how to get the machine booted. And here it is in the original operating system from, well, 1988 was the last time that that particular platter had been used. So we got there. We got this machine that looked like a complete and total basket case up and running. And it took this insane combination of really brilliant people doing reverse engineering work and original employee that used to work there and knew insane things off the top of his head. Like we got into the memory monitor and he's like, yeah, hit memory address F148 because that's the command register for the Hawk drive and we can control it from there. And he had all of these things stored in his brain. And so this massive collaborative effort brought the machine back to life. This is a fun little video that I made. So flip the power on. This is the power up procedure. Turn the terminal on. I didn't have a key, so I had to pick the lock. So we turned the power on, get the Hawk drive spun up, load up the operating system. There it is, fully loaded into the operating system. And that actual video was probably about 1.5 years old. This is how the computer looks now. So there's a lot of things going on here. We have that Hawk drive in the middle. So that's 10 megabytes of storage right there. Again, by doing this for 3 years, people come out of the woodworks. The Hawk drive on the right in the middle, that's another 10 megabytes. That came from a wonderful museum up in Pittsburgh called the Large Scale Systems Museum. There's the Phoenix drive on top. I haven't touched it yet because I'm scared of it. On the left side, we have an 8-inch floppy drive. There's also a 32 megabyte Finch drive in there. So we've got like almost 100 megabytes of storage going on this machine, which is pretty insane. We have the main data terminal on top. We have an EDS PC on the right. This is part of Centurion's story. They got bought out by EDS and they had to build these PCs. And Ross Perot came down to Centurion and said, we need a PC to compete with IBM. So Centurion got all fired up and built that. And they built about 100 examples of it. And Perot and all the guys at EDS put them on display and brought the IBM guys down and said, look, we don't need your IBM PC because we have a competitor. And IBM went, all right, what's your price point again? Like, all right, we'll do that. And they went, great. So it was just a dog and pony show to get a cheaper price point from IBM. And so they shut it down. So that's like incredibly rare. They built like 300 of those. That was purely just to get a cheaper price point out of IBM for EDS. And then on the left here, we have probably the most terrifying machine, which is an old chain printer. People that worked in these rooms back in the 70s probably remember these. Has a chain that spins at a relatively high speed with hammers that slam into it at the right time. Makes a fantastic racket and does 125 lines per minute. And that was a slow one. Fast ones could do 600 lines per minute and stuff like that. But there it is. It's fully working. It took me as a mechanic to get it up and going. And we got there through insane collaborative reverse engineering effort. But that is not the only project that I work on in that room. just here, you can see we've got a Litton mini computer. The really tall one is a Data 620. Next to it is a PDP 1144 with an Eagle drive on it. Then we have a smaller Zilog system over here on the left. There's an NEC PC 8001 above it. There's a TI 99 hiding over there in the corner. You can see there's just a bunch of projects going on. And one of the projects that I'm really, really excited about that we've been working on recently is this one, this big turquoise thing here. That's a Bendix G15. It's a full-fledged vacuum tube computer from 1956, and no joke, it weighs 1,000 pounds. That's not an exaggeration. When it showed up, Bob over at System Source sent it down to me. The box it showed up in had 1,257 pounds written on the side of it. That is a 1,000-pound computer. It's got about 460 vacuum tubes in it, somewhere around 3,200 germanium diodes. And currently, it doesn't work, but we're very, very close. It has a rotating drum memory in it that has about 7 kilobytes of storage on it. And we think that the drum itself is made out of titanium, which is pretty fancy materials for 1956. And if we get it going, which we're so close, we've actually managed to boot the machine, but it's not executing code quite yet. It knows where it needs to go to start executing code. It just, you hit go and it doesn't go there. So we got a little more troubleshooting to do on it. But if we get it going, it could quite possibly be the oldest running digital computer in North America, which is a pretty wild superlative to throw around. So that's what I'm really excited about. And there's one more project. I mean, there's another smaller Centurion that I built from scratch and pinball machines and stuff like that. But there's another project in this picture that is interesting. And that's the next one I want to kind of focus on. And that's the one that's bolted to the wall. And you'll notice it looks like there's about 250 vacuum tubes sticking out from the wall there. Well, this is a home-built vacuum tube computer. Again, about two and a half years ago, I decided that I wanted to build a computer. And so I designed and built a vacuum tube computer entirely from the ground up at home in my shop, which, now that I think about it, might mean that maybe I am an engineer? Is that what engineers, I feel like that's what engineers do, right? So, all right, let's explore this a little bit. So this all started during the pandemic. I was looking for entertaining things to watch, and I was watching Ben Eater's 8-Bit TTL computer series. Fantastic series, by the way. If you learn anything from this talk that I'm doing here, I want it to be for you to go watch Ben Eater, because he's like a huge inspiration to me. And if you have any questions about how computing works at a very low level, he can explain it better than just about anybody in the world. So I binged pretty much every video that he had ever made. And he built a computer called the SAP-1 out of 7400 series TTL logic chips. These are little ICs. I mean, you can see them on there, just like little black integrated circuits. But they're not like large scale integration. They have like 4 logic gates in them, or they have like a binary counter in them, just like building blocks. And so he made this computer out of building blocks, and I really, really wanted to do that. But because I'm next level dumb, I said, you know what, I'm going to do it out of vacuum tubes. And so this is the block diagram for the SAP-1, essentially what he built, the simplest possible one. You have some pretty simple stuff, like a 4-bit program counter in the top left. This just essentially counts up from 0 to 15, and that's whatever your instruction is. So you have 15 instructions that you can run on a loop. You have an accumulator and an adder and a subtractor, so you have an arithmetic unit, not an arithmetic logic unit. You've got 16 by 8 bytes of RAM, so you have 16 bytes of RAM, very, very small. Instruction register, output register, seems like this should be quite simple, but can you actually build this out of vacuum tubes? Right, so what I did was I sat down and I started trying to figure out what it would take to actually build something like the SAP-1 out of vacuum tubes. And if we take a look at just the program counter, this is just a binary counter that counts 4 bits from 0 to 15, which is going to be like, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0. It just counts up, right? He used a chip called the 74LS161, and this is the block diagram of the inside of an LS161. So you have 4 JK flip-flops and a boatload of logic that comes out the other side. That's a lot of effort to build just that out of vacuum tubes, because each logic gate is often going to involve one vacuum tube, and tubes are big and heavy and hot. So that chip has around 100 transistors, maybe more, maybe less. I didn't count, but I mean, that's the die shot of the chip. So if you were to delit it and take an electron microscope, or you probably don't even, this is probably at an age where you don't need electron microscope, just a good microscope will probably get you this shot. You can see that you have the different layers of silicon and you're making all the transistors. So if you've got 100 transistors for just the binary counter, we can probably realize that with about 50 vacuum tubes by using dual triodes or using germanium diodes. But that means that if we exclude the RAM and we take an average of just 50 vacuum tubes per block for these SAP1 here, that's 450 vacuum tubes just to realize what Ben Eater realized in something that was about this big, right? 450 vacuum tubes is insane. And then you've got RAM. RAM is another nightmare. Now, he doesn't have a whole lot. He's got 16 bytes. But even if you wanted to build 16 bytes out of vacuum tubes, that's another 500 tubes. So we're talking about 1,000 vacuum tubes. For reference, each vacuum tube has a filament in it. And on average, that filament pulls 0.3 amps at 6 volts. If you have 1,000 of these, you are building an arc welder just to power the dang thing. So, okay, we'll throw that out. Now, there's a caveat here. There's smarter ways to go about building these things. You can do an insane amount with diode logic. So if you're willing to use germanium diodes, which most vacuum tube computers of the era did, you can do tricky things like this. This is a full adder. So a full adder takes 2 operands in and a carry bit in, adds them all together and gives you a 2-bit result out. This is like the most fundamental part of building an arithmetic logic unit on a computer. And this is one that I designed based upon looking at documentation from IBM and Librascope and all these other companies back in the day. And it's a full adder that uses just a single tube, just a single triode. Everything else is diode logic with clamping to 0 and minus 20 volts and big voltages. And so if you're smart, you can do a huge amount with diode logic and use tubes only minimally. And that's actually what the Bendix did with the G15, and that's what Librascope did with the LGB30. But at the time, I didn't know that because I'm not all that smart. So I was just like, impossible. So let's come up with a better, smarter, faster way to do this. And so I decided to copy a IC that Motorola had built called the MC14500 or 14500 or 1445 double odd, or however you want to say it. This is essentially a 1-bit industrial control unit. You have a 1-bit data bus. You're dealing with just a single bit at a time, but it's important to note that this is not something that we would call bit slice. You can't stack multiples of these up to get wider bit widths. This is just a full-on 1-bit CPU. But it's an incredibly simple layout. So I said, you know what? I think I can get away with this. I think I can do it. But I don't like the fact that they only had a logic unit. Motorola was not able to do any arithmetic. So I decided to re-engineer their logic unit to be able to do arithmetic. So the Motorola instruction set is on the left here. And you can see all of their logic unit instructions. You got load, load complement, and complement, or complement, and exclusive NOR. And I decided to go with load, add, subtract 1, which gets everything into a known state, and NAND, or an exclusive OR. This is a pretty full-fledged arithmetic logic unit. And it's interesting what you can accomplish with just 16 instructions, because modern CPUs, particularly in the x86 architecture, have a lot more than 16. So the first step was sit down with a program called Logisim. I don't know if you guys have heard of Logisim. This is a program that lets you build logic gates. So I chose NOR gates as my primary logic gate here, and you can see almost almost everything in there is either NOR or NAND. And if you have a NOR gate and you have a NAND gate, you can build every other type of logic gate from just those. So if I want to build exclusive OR, I just use 4 NOR gates, and now I can build an exclusive OR gate. So I spent probably, well, my wife would tell you too much time building this at night. And I came up with a logic design. I said, okay, I've got a logic design. How do I get this down onto real deal stuff? So the next step was to come up with vacuum tube logic. But again, I'm next level dumb, and I tend to plus 150, minus 150 for biasing. Maybe you got a plus 260 somewhere. And if you're like licking your finger and putting it in the middle, you're going to have a bad day. And I knew I would be too dumb to not do that. So I decided to do it, something that I don't think anybody's ever done. And I decided to build this whole thing on like realistic low voltages. So the highest B plus that I've got is plus 24 volts, and I have minus 12 volts for biasing. The largest voltage potential difference on the entire thing is just 36 volts. You can like lick your full on hand and slap it, and it's not going to hurt. Well, I mean, you'll feel like an idiot and there might be sharp points, but you're not going to get shocked. So I built these logic gates based upon that, months of testing, trying to get balanced just right, which tubes work, which tubes don't work at low voltages. And I came up with these designs. On the left, we have a NAND gate. On the right, we have a NOR gate. So once I had that all squared away, it's time to start building it. And so I didn't want to order my PCBs from China because I like American manufacturing. I'm an American. So why don't I manufacture it myself? So I have a CNC mill at home, and you guys just saw a very fast time lapse. We'll see if I can get that to start again here. So there's a very fast time lapse. So essentially, I design out a circuit on an EDA program, an electronic design assistant program. I don't know what EDA stands for. I design it out, turn it into Gerbers, convert those Gerbers over to G code, load the G code into our CNC mill, and machine out my PCBs. Now, our CNC mill is kind of old, and it's meant to do like big, heavy stuff, not really small, precise stuff. So my circuits are like ridiculous here. I have 1 millimeter trace widths, which is like having a highway for a trace. It's huge. And my trace separation is 2.54 millimeters, which means I can't run traces in between pins on ICs and stuff or whatnot. But it cuts really well on the mill, and it comes out really consistent. And I can essentially come up with a design, walk out, and just do fire and forget. I can get the mill set up in 15 minutes, hit go back inside and play video games, play some Halo, flunk out of college, you know, that type of stuff. And at the end of the day, you end up with something really cool like this. That is 190 vacuum tubes all on at the same time, essentially doing our modified MC14500. It looks, I mean, you can't really see much there. So here's an actual video of what it looks like. The tubes are not directly soldered to the PCBs, don't worry. I actually have 1 millimeter pin headers in there, so the tubes are in sockets that I built from scratch. And there we go, all bolted together. It actually worked too, which is insane. It didn't even need that many bodge wires. But then I came to the realization that just the industrial control unit by itself is kind of useless and doesn't do much. You need other stuff. You need supporting stuff to go with it. I need memory. I need stored program control and all that stuff. So in their handbook here, the industrial control unit handbook, Motorola outlines what they call the minimal ICU system. And you can see right in the middle is the MC14500B. Essentially, that's what I built. So now I need to build everything else on this. So start designing the logic again, start all over, figure out what we need to plug into what needs to go where, cut more PCBs, and start designing and putting things back together. And then the real trick here is to give a presentation on it before it's complete. So that way you can say that we're still working on it, right? So there's a giant hole in the middle there where a paper tape reader is going to go. So my next step is to build a photo paper tape reader. So you can have 8-level paper tape. As it pulls through, it reads the bits off of that, executes them. That's our stored program. We have 2 bytes of memory available on it. So it's not a very good computer, but it is a computer by the strictest definition of it. And I think it's a pretty cool thing. I think that, I mean, that's pretty close to being like an engineer, right? That feels like I did some engineering. But like honestly, if I'm being honest, I mentioned this before. It was a massive group effort. Anytime I came up against a hurdle, anytime I butted my head against something that I didn't understand, YouTube commenters jumped in or Discord members. Discord is like a group chat that I have going on dedicated to the Usagi Electric channel. And so this group effort is actually what made it possible, which actually brings up a good point. I'm not a mechanic. I'm not an engineer. I do know what I am. I'm just an idiot with a camera. And so it just so happens that having a camera and creating this YouTube channel is what has allowed me to do these things, like work on potentially the oldest running digital computer in North America, or build a vacuum tube computer from scratch. It's all possible because I chose to be a filmmaker first and a hobbyist second. And now we're getting into what my daily life looks like, which is something like this. I start on Monday, I start filming and doing work. And anytime you're filming whatever it is that you're working on, the amount of time it takes to do something is like quadrupled instantly. Because I need to desolder this resistor because it's burned out. All right. Normally you just sit down and you desolder it. All right, well, hang on a sec. Let's put this here. Let me set the camera up over here. Now that looks like shit. Let's move it over to here. All right, right? So it's just like that over and over and over again. So I film and work for about 3 days, and then I start the editing process on Thursday and Friday. And then on Saturday, there's stuff that I invariably missed, and I have to film again. And then I upload on Saturday, and then I make the video live on Sunday, and then I immediately have a panic attack because I don't know what I'm going to do on the next Monday. And then also I'm like looking at the video, like, did it perform well? Did it not perform well? To give a little bit of reference, I really try to make the video experience as seamless as possible. I want it to feel like everything just kind of flows into one thing or the other. There's no jump cuts or anything like that, but you can see this is what the standard video timeline looks like. And all of this stuff on the bottom here, this is like audio clips and video clips. And you can see it's just like it's a nightmare. It's a confusing, messed up nightmare because that's what video editing is. It's a wonderful and horrible thing all at the same time. On average, I use per video about 75 to 150 different video files or video clips, and then 50 to 75 audio or image files, and then 10 to 20 audio files. And I don't do anything in RAW because I value hard drive space. So on average, every week I'm using about 30 gigabytes of storage. That's just the data that's generated from doing it this way, from the videos that I film and whatnot. So then I really try to aim for between 20 and 30 minutes on my videos. And I release a video every single week, which is a stupid, dumb kind of standard to try and hold myself to because I don't get any vacation days. That's like a 7-day work week, 52 weeks in a year, right? But my video lengths vary. The great thing about doing things on YouTube is that you don't have to adhere to exactly 25-minute episodes or 48-minute episodes because you got to flip in more. You can do however long. I've got some that go up to 38 minutes. I've got some that come down to 15 minutes. The hard and fast rule that I have is never go over 40 minutes. 40 minutes I feel is way too long. Also, I value my sanity and I don't want to edit a 40-minute video. So YouTube is a numbers game. They're constantly pushing you to make your numbers bigger. So every time you upload a video, you get this little thing right here that says top recent videos. And it's for however long your most recent video has been up for. In this case, when I took the screenshot, that video had been public for 3 days and 15 hours. And I can see immediately it performed pretty well. I got 55,000 views on it. That's pretty epic. But I can also see it's in 4th place, and that hurts. Man, I want to see it be in that #1 spot. But it can't be in the #1 spot every week. That's just impossible growth. But it means that YouTube has kind of created this environment that is constantly mentally pushing you to always be striving for that #1 spot. if you take a step back and you look at it, like this is my subscriber growth over 2 years here, January 2022 to September of 2024. And this is the total video views. And it's like a straight line, man. That's fantastic. It's just going that direction. I mean, I would like to see it go that direction, but I can't be upset with that. But every time there's a little dip in the subscribers where maybe I didn't get that many subscribers this month compared to the month previous, it hurts. I can feel it on the inside, man. So this raises the question of what does the almighty YouTube algorithm like? And if you look at some of the bigger channels like Veritasium, Smart Everyday, and Linus Tech Tips, and I've actually had the pleasure of meeting Derek from Veritasium, super nice guy. These guys are huge. You can see like Veritasium and Linus Tech Tips are 16 million subscribers. Smart Everyday is 12 million subscribers. But they have a couple of things that they all do that really kind of play into what I think the algorithm likes, is that they're very consistent. They upload on a really consistent basis, maybe not every week, but they upload maybe 30 videos a year or 35 videos a year or something like that. They have a very broad appeal with their topic, with their content, their material. It doesn't get really deep into, oh, this logic gate does this logic gate does that. It's more kind of like reading a Wikipedia page with maybe a little more depth to it. They're all family friendly, and they don't do really extremely long content. It's all 20 to 30 minutes. So I try to copy some of that though, but I think the biggest thing is a thumbnail. I think the algorithm loves a good thumbnail more than anything else. So these are at the time that I took these snapshots, these are the 4 most recent thumbnails from Veritasium on the top, Smart Everyday in the middle, Linus Tech Tips on the bottom. And there is a recurring theme in all of these thumbnails. And it's that there's a face. Like if you notice, Veritasium only has one video, which is Death, Death, Life on the top left there that doesn't have a face. And that's the only thumbnail out of the 4 most recent videos from these 3 huge dudes that don't have a face in it. So I said, maybe I need to do faces. Like maybe I need to put faces in my videos. So I've experimented with some of that. I've had some thumbnails with faces. I've had some thumbnails without faces. And I just don't get it. Like you can see here that Linus has all of these weird expressions going on, and he seems to get about the same 1.6 million views, 1.4 million views, 1.2 million views. That's a lot of views, but we're looking for differences in the numbers here. I made a video with a face, 92,000 views. And then I made one that's just like a paper tape that just says I made this, 131,000 views, one of my better videos. But I don't know what's going on. Why did that one do so well? Like, is it a well composited picture? I don't know. Ultimately, it's really easy to just fall down this rabbit hole of trying to chase what you think the algorithm likes. And so every once in a while I have to go, screw the algorithm. It's time, I got to step back and just do what I find fun. Like, don't look at the numbers. Just do what I enjoy. I got to this point of, I'm not a big YouTuber by any means, but I got to this point where I am able to live off of the income from YouTube videos because I was doing things that I thought fun. And I was building things that I thought were interesting and exciting. And I will try my best to continue to do that. Hopefully we will crack 100,000 subscribers. I say we, it's just me. It's me alone in a room with a camera, which is really crazy to have people in front of me because usually it's just like me, a camera, and nobody else. So you can do really weird, yeah. The void is much more comforting than eyes staring back at you. But hopefully we're going to crack 100,000. I'm at like 95,000 or somewhere around there. We're going to crack 100,000 before the end of the year. That's my hope. And then just keep growing, keep growing. I hope to continue to do this without ever having to go, you know, this video is sponsored by Raid Shadow Legends. Hit that subscribe button, smash that like, no, I'm not going to do that. So that's my story of who I am, where I came from. There's a lot more projects going on. We had an hour for the talk, but we wrapped it up in about 45 minutes. So does anybody have any questions? Anything you want to ask me? Anything you want to see again? Anything you want to double check? Yes, sir.
The guy that was helping you that used to work on the mini computer. Did he have any documentation left over from?
So he asked if Ken Romaine, the guy who used to work at Centurion, had any documentation left over. He did not. But because Ken Romaine helped me out with this, and because the channel started to get big, we actually got a message from a gentleman named Bud Smith, who was the co-founder of Centurion and was Ken's boss. He sent us a message, and it took us a while to kind of get our schedules to line up, but I got to go meet him. And the reason it took us a while for our schedules to line up is because he had leukemia or lymphoma, and he didn't have long. So I went to his care facility and spent an entire day with him, and he had a box of documentation, but it wasn't technical documentation. It was marketing material, pictures that he had taken to build brochures and stuff like that. And I sat down with an entire notebook, and I just wrote down the whole story from Bud's perspective. And the story of Centurion is crazy. There's like corporate espionage, and like the dude died in a Corvette doing like 100. Like the other co-founder was John Rex Warren, who was Bud's brother-in-law. He died in a Corvette doing like 140 miles an hour and on Firestone tires, which then that Corvette became part of the Firestone case in the 70s. And like the company almost went bankrupt like 4 times. They lit their warehouse on fire once. And like burned up a bunch of artwork that they had for the PCBs. So they had to like re-engineer PCBs from scratch. They went to I think it was in Vegas. There was that massive hotel fire in Vegas that killed so many people in like the mid-70s. Almost the entire Centurion personnel was in that hotel, and they just managed to get out. But if they had been in the wrong place, the company could have evaporated right there. I mean, the company, and then of course they get bought out by EDS. They become a subsidiary of EDS, and Bud kind of gets pushed out, and so he steals a bunch of technology and starts his own company called Zetron. That makes Ross Perot very angry, and then they get into this like legal battle where Ross Perot wants to just like, torpedo Bud, all of Bud's, and it's like it's this wonderful story. So I got to sit down with Bud and listen to the story, but we still haven't come across any official documentation for like any of the hardware or anything like that. So all of the schematics that we have are all stuff that we reverse engineer. That was a really long answer to your question.
No, that's awesome.
Yeah. It's yes, sir.
This on?
Yes.
So I'm fascinated. You're running 4 to 6 projects at a time. That's a lot to keep in your brain and try and pivot between these things efficiently. Talk a little bit about the mindset of going from one completely different architecture to another completely different architecture. What do you carry between them, or are they all totally, orthogonal?
So yeah, we talked a bit about this. Burnout is mostly what I'm trying to avoid. Burnout is like a real deal thing that you have to worry about. And I'm sure that all of you guys being engineers butt heads against burnout all the time. If I focus on a project every single day for months on end, I burn out on it. And then I push that project in the corner, and then I don't touch it for 6 months, 8 months. And then I go, I should really get back to that, but I don't remember where I left off. And then I don't touch it again for another 6 to 8 months. And then I go, well, now I haven't touched it for 2 years, and I certainly have no clue where I was. And then I just scrap the project and I start a new project. So the idea of juggling multiple projects was to keep me cycling through. So I'll do a Centurion video this week. And then next week, I'll do a Bendix G15 video. And then the week after that, I'll do a PDP-11 video. And then the week after that, I'll do something that strikes my fancy. And then I'll cycle back around to the Centurion. So I try to cycle through 4 projects a month. But every once in a while, you hit a roadblock. You're waiting on parts, or maybe something's incomplete and it can't go any further until that really rare piece shows up. Or maybe I'm just like sick of it. I'm just like, you know what? I need to step away from this for 2 months. So I'll just put something on the back burner for a couple months. It does require a very dramatic change in mindset, particularly going from something like, say, the Centurion mini computer, which in and of itself is a very strange computer with a very unique architecture, very unique instruction set. For example, it uses 400 bytes per sector instead of like the really common 512 bytes per sector. This was done for backwards compatibility with like streamer tapes and anyways. And so that requires a very specific mindset. And then I put that down on Saturday. I'm like, I'm done with it. And then I step on over here to the Binix G15, which is dramatically different, right? So the Centurion mini computer, yes, it's wild, but it's still an 8-bit computer. It still has, a 16-bit or an 18-bit address bus. It still has all of these things that we kind of equate with modern computing, even though they're all just slightly different. But then you step over to the Binix G15, and it's got a 29-bit instruction word. And you're like, well, what are they doing with 29 bits? Like, what do you need that many bits for? Well, okay, well, it turns out that on the Binix G15, they've got rotating drum memory. And because the rotating drum is kind of really an obtuse thing, each instruction essentially has a source location, a destination location, and a go-to, where the next instruction is at. So when you build your 29-bit instruction word, you're telling it where to pick up some data off of the drum, what to do with it, where to put that data back down on the drum, and then where on the drum the next instruction is located. So that kind of like mental shift is like very stark, but actually it works out that it's so dramatically different that you don't end up getting them confused. I'm never like, oh, that's an 8-bit computer, but I got my instructions confused, right? You don't get an 8-bit and 29-bit instruction confused. But it does require a big shift. The thing that helps a lot is that the people that are helping with these projects, Ken Romaine on the Centurion mini computer who used to work there. There's another guy, Lloyd Hazley, who is helping me with the Binix G15. He actually used to write programs for the Binix G15 when he was in high school, because he was in high school in the 70s. And at that point in time, this kind of goes back to what we were saying, the Binix G15 was just old and nobody wanted them. So high schools were like getting them for free. And so nobody wanted to play with this old hot vacuum tube computer. So that was how Lloyd started working with it. And that's all, like Lloyd is hyper-focused on that. And Ken is hyper-focused on this. So when I switch between the two, oftentimes I'll reach out to one of those guys and they'll help me get back into the groove of, okay, we're on this boat now. We're doing this thing now. And then your brain kind of goes back and forth between the two. Interestingly, it's a bit like language in that way. Does anybody here speak 2 languages? What? Oh my gosh. Holy cow. What languages do we have? We got English, obviously. What else we got? Huh?
Bangla?
Bangla? Are you Indian?
Yeah, no, Bangladeshi.
Oh, Bangladesh. Okay.
Indian.
Spanish in here? Any Spanish? Maybe is that the Texan in me coming out? I just expect Spanish to be like. Oh, we got some Mandarin in the back, right? All right, so you guys are bilingual. When you switch back and forth between English and your other language, whether it be Mandarin or Bangla or, in my case, Japanese, do you feel like it's 2 different languages? Does it feel like 2 completely separate things?
Well, for me, my Mandarin isn't best, so
Okay. Okay.
But yeah, it's different. So like growing up, I still Mandarin. Growing up, so then I physically had to apply myself to elementary school to not speak Mandarin in like kindergarten or first grade.
Okay. When you're speaking English, do you find yourself sometimes knowing the Mandarin word for something, but not the English word? And vice versa? Yeah, that happens all the time for me too. But I rarely speak Japanese to somebody that I know doesn't speak Japanese. And I rarely speak English to somebody that I know that doesn't speak English. I mean, if I were in Japan, for example. So there's a good kind of separation up there. But it's not one that I'm like cognizant of. It kind of happens automatically. And when I think about the 2 languages that I speak, it doesn't feel like 2 separate entities. It feels like one large collection of vocabulary. And when I'm talking to you, I use this collection of vocabulary. When I'm talking to my angry wife, I use this collection of vocabulary, which often involves a lot of "I'm very sorry," stuff like that, right? So it's the human brain is kind of fascinating in that you don't have to think about that switch happening. And the same thing happens when I'm switching between kind of computer architectures. I don't really need to think about the switch from happening. I just know that when I'm looking at this collection of blue, I need to think in this architecture. And when I'm looking at this collection of teal, I need to think in this architecture. There's a lot of times where I'm just like, I hate both of these. I'm going to go inside and not do either of them.
All right, other questions from the audience?
Yes, sir.
You have a hard time getting them? There's still people manufacturing them?
So there are, so I'm, if nobody else could hear, he asked if we could still find vacuum tubes. Are they hard to get? The ones that I use are all what we call pulls. They all came out of, not P-O-L-L-S, P-U-L-L-S. So they all got pulled out of like radios and TVs and stuff like that. There are people that are still making vacuum tubes, but it's not for this kind of like large scale stuff that I'm doing. They're building them for the hi-fi community. So hi-fi audio is still massive. And they love vacuum tubes because vacuum tubes have a very, very wonderful linear range and they distort in a very known way that gives a good warm sound. And I don't know, I'm deaf in one ear, so it's all lost on me. But what that means is that oftentimes they'll pay like $150 for 2 matched 12AX7s. I'm like, I need 190 tubes, man. I'm not paying $150 per tube, right? But it turns out that in the 1940s, 50s, and even pushing into the 60s, if they were being cheap, they made a lot of TVs, man. They made a lot of cheap radios too. And these came with pentodes usually. So the hi-fi guys really love the triodes because they're very linear. But are you familiar with the difference between like pentodes, triodes, and tetrodes?
For logic, you don't need, you just need something to turn on, turn off.
Exactly. So with the triode, you have getting into a bit of how vacuum tubes are made. You've got an anode, you've got a cathode, you've got a grid in the middle. And the cathode gets like phenomenally hot because you've got a filament on there getting it really hot. And when it gets hot, the electrons boil off of it into kind of an electron cloud. And if you give those electrons a positive potential to go towards, they go there, right? So you put the anode at a positive potential, the cathode is at a negative potential, and electrons flow in one direction, but they don't flow in the opposite direction. If I put the anode at a negative potential and the cathode at a positive potential, well, the anode's cold, so the electrons don't boil off. So we've created a diode, essentially, right? So if we put what they call a control grid in the middle, I can, essentially like a valve, I mean, in Europe, they call them valves. You can change the potential of that control grid in the middle with relation to the cathode to allow more and more electrons to pass through. And so this is that linear region of triodes that the hi-fi guys really like because they can just kind of crank up or crank down the electrons that are passing through. And so that's how they're kind of controlling the audio signal that's coming through. But if you're trying to build digital logic, linear is awful. You don't want linear. You want 0 or 1, right? But also in many other situations, it turned out that you wanted something that had a pretty sharp cutoff. You didn't want this ramp. You wanted a ramp that looked like that. So they added in other grids in the middle to help them do stuff. So in a pentode, you have 3 grids in the middle. You've got cathode on the bottom, anode on the top, then you've got control grid, screen grid, and suppressor grid. And the control grid is really tightly wound, and that's controlling whether the electrons can flow or not. The screen grid is a little looser wound, and you tie it to a high positive potential, and it acts like an electron accelerator. Whenever the electrons hit the plate, or the anode at the top, the anode is now being pulled down to a low level. When that happens, the potential of the anode becomes much lower. The attractive force of the anode on those electrons also becomes lower. So it attracts less electrons. And if it's attracting less electrons, well, the potential now goes up again. And so triodes can fall into this kind of weird oscillation if you're trying to get them into full saturation. So if you have that screen grid, it's like an electron accelerator. The electrons go flying up towards the anode no matter what. And then when they hit the anode, sometimes they hit with such force they knock off other electrons. And those electrons can maybe get gobbled up by the screen grid, or even go as low as the control grid or something like that and get gobbled up by them. So you have the suppressor grid with a low potential to keep them up around the anode. But because you have these extra grids on there, you can end up with a really nice, sharp change, right? And they call them sharp cutoff pentodes. And these were really popular for in TVs for something. I don't know, TVs are analog black magic, particularly TVs in the 1950s. But droves in cheap TVs, which means that there's like still millions of them out there. So
A bunch of old.
no, there's as with anything, there's an XKCD comic about this where you could put two guys in a, I don't know, anyways. There's a group of people that are doing that buy old stuff, pull all the tubes out of them, categorize them, and then resell them. And so I kind of set a rule that said I would not buy any vacuum tubes unless I could get them for cheaper than 80 cents a tube. And it turns out that the 6AU6 sharp cutoff pentode first worked really well at low voltage. I tested probably about 50 or 60 different vacuum tubes at low voltages at 24 volts, and I even tried 18 volts and down to as low as 12 volts. 24 volts seemed to be like a really good compromise for low voltage. And some of them were like trash, garbage, would not do anything at 24 volts. But the 6AU6 was brilliant. I was getting logic highs. Well, logic high, you're in cutoff, so your pull-up resistor pulls you to 24 volts. And I was getting logic lows down at like 2 volts. Whereas, some other pentodes, I was getting logic lows at like 12 volts or something like that. So I was like, if I have a 22 volt span between logic high and logic low, that gives me a ton of headroom for tubes that maybe have bad emission or getting old or tired. And it turns out that 6AU6 was a really popular tube in TVs. And so I have 2,000 of them at home now. And so I tend to avoid double triodes because, so a double triode is just 2 triodes in a single glass envelope. And you have 9 pins that allows you to control those 2 triodes separately. The pentodes that I'm using, the sharp cutoff 6AU6s that I'm using, are just 1 pentode in a smaller 7-pin envelope. So it's a smaller vacuum tube. I try to avoid the double triodes because the hi-fi guys are gobbling them up, like the 6DJ8s, the 12AX7s, AU7s, the 12AT7s, AV7s. It doesn't matter if it's a 12 something something 7. The hi-fi guys have driven the price through the roof. But the hi-fi guys have no use for these sharp cutoff pentodes. So a lot of times the hi-fi guys will buy an unknown tube lot, unsorted. So they'll buy like 600 tubes in this box, and they'll go through and pick out the 15 or 20 that they really like, and then they'll sell off the rest to idiots like me that are like, yeah, I want 400 tubes, what am I doing these? Right? And then you end up with, I think I've got 2,000 of just the 6AU6, but I think in total I've probably got 3,000 or 4,000 vacuum tubes at home. So yes, there are people, that was a really long way to answer your question, but yes, there are people who are still making vacuum tubes, but it's a lot cheaper and easier just to get new old stock, or not new old stock, just to get used tubes. And if you're using them for digital stuff like I'm doing, and you design your circuits in such a way that you have a ton of headroom, even as the tube ages and emission gets worse and worse due to cathode poisoning or cathode stripping or any of that kind of weird stuff, maybe my logic low only comes down to 5 volts or 6 volts or 7 volts, but pretty much anything below 10 volts is an acceptable logic low in my design. So I can use tubes that are like really kind of on their last legs, and my vacuum tube computer is just like, whatever, I don't care, just keeps going, right? So that's quite lucky. No, so this is a good question both for the home built one that I'm doing and the Bendix G15, because they both have tubes. The hardest time on a vacuum tube is when you are powering it up. So filaments, both in like everything's LEDs these days, filaments both in like light bulbs, but also in like the filaments that they have in vacuum tubes have an incredibly low resistance when they're cold. Am I getting that right? Yeah, an incredibly low resistance when they're cold, but as they warm up, their resistance comes up. So your inrush current is like ridiculously high until you get some heat into the vacuum tubes for that filament resistance to come up and the current through that filament to come down. But that means that if you just slap your full on 6 volts, 120 amps or whatever through all of these filaments at once, they're getting a lot more current than they're ready for like 3 or 4 seconds until their temperature comes up. And that can blow the filament, that can pop the filament. So I do kind of what Bendix does as well. And we soft start it. I did it because my power supplies were like, no, you've got a dead short, man. I'm not powering that up. Bendix did it because they've got 460 vacuum tubes and it's a longevity thing. They're like on the filament transformer on the Bendix is about like that big, and it has literal jumper cables going to the doors for the filament power. And the way they do it is they have these huge ceramic resistors, and they've got 4 of them, but they're in series. So they've got them two and two, and these are in series with the primary of the filament transformer. So that's like dropping the voltage that the filaments see initially down to about 1 volt and limiting the current that can flow through it. And they do that for about 20 seconds, and then they cycle one of them out. They shunt across it. And then that bumps it from about 1.5 volts up to about 3.5 volts. And then that allows the filaments to get a little more heat in them. They do that for another 20 seconds, and then they shunt that last one out. And then the filaments can warm up fully to the end. I do essentially the same thing, only I do it with just a single shunt. I have a 100-watt 1 ohm resistor, and I run everything through that until the filaments get warm enough. It goes for about 10 seconds, and then it shunts across that, and then the filaments warm up the rest of the way. And by doing a soft start, it keeps your inrush current to less insane levels, but also it helps lengthen the life of the vacuum tubes. I'm powering all of my filaments off of I only wanted 24 volts and minus 12 volts on my entire machine, but all of the filaments are 6 volts. So I'm powering the filaments by stringing them up in series. So I'll put 4 in series and run them off of that main 24 volts that's powering all the logic, or I'll put 2 of them in series and power them off of the negative 12 volts. Like they don't care whether it's negative or positive, voltage is voltage. But what that means is that, like when I was flipping it on, my 24 volt power supply was trying to supply like 25, 26 amps for the inrush current initially. And it was just like, it was cycling. Because I'm using like a modern switch mode power supply to do it. So I'd be like, flip the switch on, and it'd be like, nope, not doing that. So it wouldn't power up. So I had to do the soft start so that my power supply would be happy. And so it jumps up to about like 19 amps at 24 volts, and then it kind of falls down, and then it cycles back up to about 19 amps, and then it ultimately settles in at about like 14 amps, I think, off the 24 volt rail.
Awesome. Let's thank our speaker. This has been great. Thank you, everyone. Looking forward to next month's talk on People's Co-op Energy for those that can make it. We do have a YouTube webpage where this will be played along with all of our previous videos. If anyone has questions, you can always email the board, IEEE Southern Minnesota, something like that.
SMN.
SMN?
Yeah,
I don't know. Look on our webpage or on our YouTube page.